All right, sweet. All right, I'm Aidan. This is my tea time talk about my thesis. I don't know, I'm a master's student here. Yeah, so I'm going to talk about deflection routing using Bandits. Yeah, so here's a quick outline of what I'll be talking about. So this is more high level, so I'm going to talk about the routing problem briefly, then the solution method I use, as well as the problem setting. Yeah. All right, so to start with the routing problem, so first we're going to go over what a communication network is, what routing is, what deflection routing is, and then just one thing about how the problem itself is non-stationary. All right. So to start here, like what's a communication network? If I say network in this talk, I probably forgot to add the communication before it. So I'm not going to talk about neural networks. But so a communication network is like here on the right here is just like an example. It's basically a graph. So you have nodes, which are switches, and then edges, which are links. And the whole point of it is trying to move data from different switches to each other and then across the links. So on that, like the data itself is the network traffic. And you can think of the network traffic is going to be a set of flows. And a flow is a source and destination pair. So let's say down here on the bottom left, and then up here on the top, let's say bottom left is the source, and the top is the destination. The source here will generate packets according to some, let's say, statistical process, and they will enter the network, and then the point, and then hopefully they'll arrive at the destination up here.
Are all flows single source, single destination, or might you have the one flow going to,
We're assuming single source, single destination.
Okay.
Yeah.
Thank you.
And it's bufferless and bidirectional links.
I don't know if this matters, but does a flow specify the route?
No, just a source destination. Yeah. Okay, so then we're going to talk. So then routing. So routing is the problem of actually moving it throughout the network. So typically, like ideally, you'd want to take the shortest path because you want it there as quickly as possible. But that's not always possible. So here we have an example. The red arrows are from the source to the destination, and we can see it takes what we'll call here is a hop. So it goes from the source to that next one. So that's one hop and another one, and then we have 3 hops, and we get to our destination. And it's taking the shortest path there. Here, but one thing that might happen is you might not have any path available. So if you're in the bottom right here, and you're a packet, or like there's a packet at this switch, and you want to move it anywhere, like you want to move it somewhere. Let's say these 2 links here are not available because another packet is they're currently in use. So we'll just say so like a packet's being put on them, so you can't put your packet on them. And in that case, you might have to drop the packet, or you'd have to drop the packet.
I have a couple other questions. Sorry, just clarification.
Yeah.
When you say shortest, you mean shortest in terms of time? Shortest in terms of hop count?
I'm assuming all links are the same, so it's hop count.
Sometimes, it could be a big fat flow.
Yeah, no. So all the flows are the same, all the links are the same. I just care about hop counts. There's no buffers. Yeah. Okay, yeah. So then if you're here, then you have to drop the packet, and you don't want to do that. Because then likely whatever that packet comes from wants to send it, and it'd have to send it again. So that's bad. And then so now we'll talk about. So I'm going to jump a bit into kind of more like a way to talk about this in RL. So we're going to talk about action. So at a switch, so we have this center switch here. It's surrounded by other switches, and when it needs to route, it has to select its actions are selecting a neighboring switch. So all those red links are the switches. Because with the properties of this problem, you want to take those actions immediately, because if you wait, then you're kind of wasting the resources. Like you could have sent it on the link before, and you're kind of wasting the network resources, and you'll get less through the network. So you want to take actions immediately. And ideally, you'd want to have minimal computational overhead in selecting actions. Okay, so now we're going to talk about deflection. So deflection it's pretty simple. So let's say you have a source and a destination here. You'd ideally send it along the shortest path, but sometimes that's not possible. So let's say for whatever reason, this link isn't available, so you can't send it there. So instead, what you might do is you might take a longer path and so like sending it not along that shortest path is called deflection. And the idea is that you'll take longer, but it'll still arrive. So you're trading off time for delivery. So we're going to assume that you want to, like, that's a fair trade-off that you want to make. Right. So now we'll just quickly talk about how this problem is non-stationary. So earlier I talked about how we have flows, they're the source destination pairs. And so we can assume, so in this network here on the right, all the bolded links here are going to be congested, which means they're just in high demand. So there's a higher probability that they won't be available. So if you're going from the bottom left here to the top again, maybe, like right now, it's probably best to go to the right here and then up to the top.
Sorry, my man said I shouldn't ask any more questions. Normally with deflection routing, you deflect around, you have a link that you can't go through, and you deflect around, but that packet will come back, the original definition of it.
Yeah.
Switch, and then you have alternate things, but it looks like you were calling deflection more.
Yeah.
It's just choosing an alternate path.
Yeah, I'm using it generally as in like as in like that first part of just not taking that action,
Yeah,
and then you might take a
be
different route.
careful about that, because some of us old guys are gonna see deflection routing as in the old.
Yeah. So you're not necessarily going back here in the way that I'm using it.
Okay, thank you.
Okay, yeah. So here we have bottom left to the top. Sorry. So here the left half is really congested. That means you're more likely to drop a packet, so you want to go right and then up. So that's going to happen at some point in time in the network, but then over time the flows will change. They have a limited life, and so then later on what might happen is it might change to this. So originally, the best policy going from like the bottom left to the top would be go right and up, but now as we can see, that's more congested, and the shortest path is now available if you go straight and then if you go up and then to the right. So then you want to be able to adapt to changes like that. Yeah, so all right, so now we'll briefly go over the solution method. So in here, I use contextual bandits, and then I also approach it as a multi-agent problem. Okay, yeah, so I choose to use bandits because they're sufficient, as I'm going to assume that there is no relationship from the current to the next state, and the state is going to be defined by the packet, because every time you get a packet, you have to make a decision. So I'm going to assume that, so the packet, the main part of the state from the packet, the most important piece of information is going to be the destination, because the whole point is to move packets to destination. So then because of that, I assume that and I feel like this is a fair assumption to make, that the destination is somewhat random. So then we'll treat that as contextual or as a bandit problem. I do need context because the actions I have to take have to be respective of their destination. If I don't do that, then I can't learn a good policy, or it might, depending on the architecture, it might not be possible. But we'll just briefly state that. And then I just use linear UCD. I chose like a linear algorithm just because linear algorithms are generally more reliable, and you can assume they have a lower computational cost, which kind of fits the problem where you don't have a lot of compute and you need to take actions quickly. Yeah, so then so I'm approaching this in a multi-agent as a multi-agent problem. So here we have a network here, and each of these switches contains its own agent. So they're going to have to cooperate and work together. And because they're independent agents, this should allow them to more quickly adapt, because they're able to learn more. They'll be able to get feedback more quickly. So then I just have 2 points here of why I don't think central agents are good, or at least I don't think they're. I don't like them for this problem, we'll say. So one idea you might have is like, why don't I have a central agent to select the actions? But the problem with a central agent to select actions is, since you're on a network and you're moving stuff as fast as possible, you would have to move information to the central agent to give it your state and then have it send your action back. And of course, that takes more time than it would take you to just send the packet. So in that sense, that's not feasible, having a central agent. The other option is to have like a central agent that learns either an individualized policy or learns some policy for the network. That is possible, but that would not be as adaptive. It'd be slower to react, and it would take up a lot of resources that could be spent instead sending packets. So we're trading, so you'd have to make sure that the added cost of distributing your policy that is lower than the added benefit of hopefully a more powerful policy if you were to do that. So in that case, just say each switch is its own agent. It does I don't know. I feel like it makes the problem a bit easier to solve. All right. So then we're going to talk about the problem setting here. So I'm just going to a brief overview of like how I approach the routing as a bandit problem, delayed feedback, the reward I use, and then a bit on the kind of properties of the problem itself, the network routing problem itself, which is the frequency of interactions, how I analyze it, and then a little different way to view the problem. So we've kind of alluded to this. I kind of alluded to this earlier in the talk. So we have a network here. Let's say our agent is the one in the middle here, red. The actions are just going to be these red lines here. And then the context is going to be based on the packet's destination, but it's not limited to. So in how I've been approaching this problem, it's bufferless, but maybe if you had buffers, you'd want that in the context. And then the reward is just the efficiency of the route, which is just how many of these hops it takes. Okay. So then just one thing that you have to be aware, I had to be aware of in this problem is that you have delayed feedback. So when a switch takes an action, it can't, unless something would happen where that packet was immediately dropped, which is not the case for me. You're not going to get any feedback until at least it arrives, or no feedback can be generated until at least it arrives at the next switch. So if we have switch 1 here and switch 2. And so we're just looking at the actions that where 1 sends packets to 2. We can see we have action 1 at the top, and then it takes some time. So vertically is time as you go down. And so we can see action 1 takes some time to get to 2. And in that time, about the time, action 2 is taken, and then 2 gets packet 1, and let's say it is able to generate a reward for it, then it's going to send it back. But of course, that takes time. And in that time, switch 1 has taken another action. So in this case, we have to make sure we separate our action selection and our updating to two independent components. And we just have to be aware that they're going to be delayed, and you're going to have multiple actions, or you're likely to have multiple actions before you get any feedback. Yeah. Yes.
Is the critical action for the same state?
It could be the same. It could be different states. Yeah, it'd be likely different states.
I see. So it will only send one package to one potential next node.
It will send as many as it can. It'll just get feedback at some point in the future. It doesn't. You don't know when.
Send the same package to multiple adjacent nodes.
These are separate. So each action is like a new packet.
Right. Then,
Yeah.
Does the one package get sent multiple times?
No.
Oh.
So let's say 1 here is generating the packets. It generates a packet and then it sends it to 2, and maybe it generates another packet and it sends it off elsewhere. And then it generates another one, it sends it to 2, or maybe and then another one comes in and then it sends it to 2. So the packets can be from anywhere. So the state itself can be anything. All this is to say, so packets are coming into a switch, it makes a decision, and then and then at some point in the future, it will get feedback.
I see. Then does the feedback is a one-to-one respondent to the actions?
Yeah, generally you'd want. We'll go with yes. With how I do it, yes. Yeah. this is more abstractly within the problem itself. Like this is the best case is getting feedback immediately. Actually, yeah, we'll just jump to the next slide because we're going to talk about reward here. So this is more related to it. Okay, so like I said earlier, when I was talking about how I formulated the problem, the reward was the efficiency of the packet delivery. So I'm defining that as over here on the right, which is the minimum number of hops, which is those jumps through the network. So down, so this is one hop over that, and I assume all switches have access to the minimum of hops to every destination. And just that divided by the actual number of hops. So if you send a packet from, so if I'm a switch, I have a packet, I take an action, it either eventually gets dropped or it arrives at its destination. From that, I know the number of hops it took to its destination that can be sent back to me. Or if it gets dropped, maybe like it gets sent back to me that it took an infinite number of hops, and so then this becomes 0. So that's great and all, but the problem is then I'd have to like track every single action of a packet throughout its lifetime, and that has a cost. And from earlier experiments, I wasn't able to. It's probably possible to learn from this, but I wasn't able to get it to learn from this. And of course, any sort of adaptation will be slow. So then instead, what I do is I bootstrap. I have a reward that's bootstrapped. So if I go from one switch to another, I can just send back the action value, and I can assume that that's the reward that switch will get. It obviously is not going to be it, but we'll assume that it's a good enough estimate. And so this reduces the overhead and of sending the entire path back and tracking everything. And then this doesn't really, you don't need to look too much, but then we can rewrite it in this form, assuming these action values are accurate, and then we get the same reward. Yes.
I have another question, sorry. When you have a really large and dynamic network,
Yes.
this min hops is going to be a difficult quantity to.
Yeah, so we assume,
Yes,
if it's big enough, then you have to track all that.
Assumptions about the topology of your network or the size of it or something where you can.
We're just.
With, good high confidence that you know what min hops is.
Yeah, so we assume we have it, which, yeah, if a network is large enough, then that does become a problem.
Have you thought of alternate ways of setting up the work when you don't know it, so you can still use this algorithm and that type of a network? I'm just curious.
I haven't, but I guess there's probably ways where you could like aggregate destinations or something. Like it's not gonna be as accurate. I don't know if it'd work, but there might be ways to estimate it. Yeah.
Sorry, so I know you said not to look at that too closely, but could you just explain? Like, is that the Q value of the next?
Yeah. So yeah, there's I grabbed these from two different sources, so they don't match up perfectly. But yeah, so this is the minimum hops of 1 here and here. This Q value here is after, once it arrives at 2 selects an action, and from that it knows the value of that action, and then it sends that back to 1. So it's after it selected an action, and then it sends it back, and then on the bottom we just have the minimum hops. You assume you know the minimum hops of both to a destination of both yourself and the neighbor. Yeah, so and you can just get that from taking the reward of 1 and the reward of 2 and just playing around with it. And this is actually supposed to be, this is an estimate, so this, if you were to do it, this is the reward of 2, and this is also the reward of 2. Yeah. So, and then because this is like a multi-agent, like a cooperative multi-agent problem, we're going to assume that this is going to that this will work and there'll be cooperation, because each agent minimizing its own reward will inherently help, or we assume is going to, minimize the reward of the other agents. All right. So just gonna, now I'm just gonna talk about like, I guess a property of the problem itself, where the frequency of interactions is, we'll say, semi-random. So like normally, if you're like trying to look at an RL algorithm, you use time steps, and like maybe you have, your time steps ideally would be at like consistent intervals. And if you have multiple agents, they'd hopefully be like consistency between them. But in this problem, that's not true, both like within an agent and also between agents. So one agent might just not see many packets because it's in a part of the network that's not used. And that can change with time. And then obviously packets aren't synchronized between each other. They're just at random real times. So in this case, whenever, if you want to, when I want to analyze this problem, I need to think about real time, not time steps for most cases. And then, so the packets are dictating when these interactions happen. And I just have to look at it in a time, like over real time.
So what are the black lines versus the red?
Oh yeah, sorry, let me explain this. So each of the black lines, so let's say we have up here, we've got switch 1, switch 2, switch 3. This is a sample of 3 switches. And each of those black lines is when it has to take an action. So when a packet arrives and it has to take an action. And then the red lines are an example of like how you could cut up the time to then have a perspective of what's going on. So maybe you want to look at like, because you can't look at the exact time steps, you'll like look over this and you'll be like, okay, here's whatever metrics. Like let's say I'm curious about reward. So then I'd like maybe average the reward over this period of time that they receive. And then I can see for each agent how much reward they get at that point in time. And then I could get like a learning curve out of that. Or I can do with any other metric. All right, so this kind of continuation of the last slide. In terms of analyzing it, so anytime, as I said previously, sampling has to be done over real-time intervals. So that's like those red bars within the previous plot or the previous slide, because there's no synchronization, both like within and between agents. And then any metrics that we need or that I can use will have to be aggregated in some way over that period of time, and maybe I do it over agents or something else. So I have like two plots from some experiments that I ran. So up here at the top, so we're just looking at packet loss. So that's when a packet gets dropped. You want that to be 0. You want that to be like ideally very very small. So this is on like a 16 by 16 grid. And I just ran it I simulated 2000 seconds, which is kind of arbitrary. I just ran it for some amount of time. And you can see, and so at every point in time, it looks at all the packets that were generated and then all the packets that were dropped. And then I get this packet loss metric. So it's just like a networking metric that I can use to look at it and understand how well it's doing. But this is across, this is across all agents. So I just know as a whole, it's able to learn and it's kind of solving the problem, and that's great. But I don't know about like the individual performance. So down at the bottom here, I have like I'll try and explain this plot here. So I have a heat map. And so I said earlier, this is a 16 by 16 grid. So we can imagine each of these squares is a different switch, and they're connected to the switches above and to the, above, below, and then to the left and right of them. And so this is just like how busy their links are, which is just a metric of saying like how often, out of a certain amount of time, how often are they taking actions? And ideally you want that, pretty low. Well, assuming you're able to like achieve other good metrics, you want that low and distributed. And this is just a way to say that this is just a way that I can look at it in terms of like an individual agent's performance. So here I just looked at the last 500 seconds and I have a metric of that. So it's not good to look over time, but it's good to look over different agents. All right. And then this is just like an interesting little perspective that I got when I was talking to someone. So the way I look at the problem is like it's based on a switch. Each of those switches is their own agent, and then they take, and therefore it's a bandit problem and they take their actions. You can turn this into an MDP, just very similar to a classic random walk, where like we can pretend that this isn't really feasible, but we can pretend that each packet is its own agent and it's moving around the environment. And then therefore you can just get like a normal like TD update as you move around. So you go from, state 1 to state 2 and so on. And then it turns into an RL problem. And there might be a way that you can turn this into, make this an actually useful formulation if you were to somehow like distribute the policy across all the switches. Yeah, so I guess just like in just wrapping this up, so it's, you know, I approached the routing problem using deflection routing and as like a multi-agent contextual bandit problem. And then there's just some interesting things with handling, analyzing it through the asynchronicity of the actions and the delayed rewards, and then the between agent and within agent interactions.
How are you representing the nodes for Bandit? Is it one hot coding?
Oh, like the destination or like the context?
Yeah, the context includes the destination, which is like a node, so that needs to be represented.
Yeah, so how do I want to say this? I aggregate or I have a way of representing the destination where it's not the individual destination, but I just have like basically a one hot encoding of like, this is the general area you're going to.
And then how big are like the graphs usually, like or the networks?
So I've done the 16 by 16. Right now, most of what I'm doing is just like 8 by 8 because it's a lot quicker. But yeah, so 8 by 8 or 16 by 16. Right now, it's just grids.
And then one smaller question. Sorry. Are there like non-learning baselines that are used? Like I don't know what do conventional networks? How do they run packets? Like random?
So what they might do is they might do like an offline every, let's say 15 minutes, collect some data, look at it, and then optimize over that and figure out like for those last 15 minutes, what's the best policy, and then distribute that as like a lookup table. Yeah.
That isn't how they did it initially. It was an adaptive algorithm. But now, like Aidan is saying, you know, big networks, they do something called traffic engineering, which is sort of routing, but at a very long time scale. So they collect information from all parts of the network, and then they start to analyze that, and then they lay down what the routes will be, and those may last, they says for 10 or 15 minutes, but that is not how, smaller networks, never, mobile networks, never, but for large things like the internet, yeah, that's how it's operating now, but it didn't.
And more on the representation side, so you mentioned initially that there is some sort of congestion which might change the optimal, like the shortest route over time, right? So how do the agents, the individual switches see this congestion? Like
so they won't. I guess through like they'll learn about it through the rewards that they get, or is it?
It's not through their.
It's not explicitly given.
It's not part of the context. No.
Yeah. So yeah, they just see the packets and they, you know, and then they'll learn that action isn't as good anymore, and they'll switch something else.
How do you simulate that congestion?
So I use like it's not just it's I can't remember, like a modified Poisson process where I change the set of flows, and each of the flows generates using a Poisson process, and it generates packets. So I have like a simulator that simulates all the packets and all the nodes, and it is moving like a discrete event simulator and just moving things throughout. Yeah. Is that right?
Oh, can you go over the like 16 by 16 figure again? Like,
Yeah.
What does each kind of
So each square is an agent.
Is an agent.
Yeah.
So they're like 256 agents.
Yeah.
So does the kind of like geometric kind of have some meaning, or
As in like, why is it this shape?
yes?
Because it's easy to generate and test on. And I don't know, it provides like it's easy to look at because it's two-dimensional, and then you have like a decent number of actions. It's kind of generous to the problem.
Connected to the ones with the edges.
Yeah. So it is kind of generous in the sense that you can usually move around and find a path there. Yeah, Alex.
So the shape of the heat map.
Yeah.
Does this mean that the nodes in the center, the lighter colored ones, are used more?
Yeah. So they'll see a lot more. Yeah. So they're gonna have a lot more interactions. So you'd probably, I don't know, this is like basically 0%, and this is, I don't know, 20%. So I'd say, you know, let's pretend that's 1%, and there's 20 times more interactions at that, like packets that sees.
And we also have a metric which shows whether like how close the learned routes are to the shortest routes or something like that.
Yeah, I do have stuff like that. I don't have it here like easily available, but yeah, unfortunately not to show you right now. Yeah. Diego, I think you.
I was just wondering how are distributed the starting and destination points.
How
Like,
dis
this plot here will change depending on where like the targets.
Yeah, so there is like this is averaged over over the last 500 seconds there. So it's gonna be like pretty smooth. So in this sense, it's just good for telling me like how well they spread out, which is generally a good thing you want to do. If I did like a smaller, then we'd probably see more concentrated areas outside of just the middle. So if I did over like a shorter period of time of like, let's say 20 seconds. Yeah. Does that, okay, Fernando?
You mentioned that you are making the assumption that the way that you set up the reward function
Yeah,
will guarantee that agents are going to contribute with each other.
yeah,
Are going to cooperate.
yeah.
How reasonable is that assumption?
Honestly, I'm not too sure. Like, I guess good enough because it works, but yeah, I'm not entirely sure. Because like you could, I don't know, maybe because like the rewards are delayed, it kind of like smooths stuff out and any sort of change will be slow. I mean, I'm just thinking like the worst case is like some sort of like weird synchronization where like two agents enforce bad actions on each other, which that might happen. Like I think there's no reason to say that wouldn't happen, but maybe if like the updates are small enough that wouldn't happen. I really don't know. I don't think I can. Maybe someone else would be able to say if you can make any guarantees, but I'm not going to make any claims like that. Yeah, I can just say like it seems to work or well enough.
Do you have some idea of how many actions might be taken between you taking the action and receiving the corresponding reward? That sort of determines how hard the problem is.
Yeah. Actually don't look at that. That'd be interesting. It'd probably be within like, well, it'd be, I'm gonna guess like 0 to 100. You know, it shouldn't be more than, although I have, so one thing I've tested with, let's just give me something here. Okay. So if we have like a network here, of course, it's going to take time to move packets from one switch to another. So what I did some experiments where I changed that amount of time and I increased it by like a factor of 100 between like 3 different values. And I didn't see any difference in performance. So it seems to not affect it, at least from the values that I chose. Yeah. So I guess like, I guess maybe since like the lower values were good, that might indicate maybe the reward is good for not letting bad synchronization happen. But yeah.
This is more of an idea, maybe something that might be helpful. So I know that there's some literature for bandits that have very, like maybe bandits that don't see all of their rewards and stuff like that. And there was some work showing that you actually don't need to update your estimate of the unknown parameter, like after every round. So you can do it after very, very few rounds, right? Like not every many rounds.
Okay. So
and like it really gives you almost the same performance as if you had done the update after every round.
okay, so kind of like that kind of like explains why like I can increase that delay and it seems to be fine.
Delay, and maybe you can even say that I don't even need to send all the feedback back.
Yeah,
I'll
just
send
enough.
One reward out of it.
Yeah. That is one thing that I want to look into is doing like not updating all actions. Because of course, like every time I do an update, I need to like if we just go back here, I need to like send back, you know, the action value, and that obviously has a cost. So if I can do less of that, that's even better. Yeah, that's interesting. I'll bug you later. Yeah. Okay, yeah. All right.
I just know that is okay.
Okay, I'll look for it then. Yeah. Any other Farham?
So if the problem is kind of cost to goal, as in how many hops you have to make to reach the goal,
Yeah.
is it not possible to, instead of min hop over hops, use a -1%, and then that would need that
Um,
mean hop number.
so maybe if you're approaching a certain way, but if you want to like approximate over different like between destinations, then you can't do that, because like then if you're going like 1 hop away versus 10 hops away, you've got a difference of like a factor of 10 in your reward. So that's why I do like a ratio instead, is that then I don't have to worry about how far it's actually going. I just assume that I want to, I guess I'm kind of treating like every distance the same, which maybe is not the best thing to do, but
The problem with the scale of the reward then?
yeah. But I think, well, and also with like any sort of, if you like any sort of function approximation, because then, yeah, I think, yeah, I don't know. I can't remember. I remember thinking about that and being really worried. I never tested anything like that, but being really worried that it would just like struggle to get off the ground, just in how it like evaluates different packets. Yeah. Right. Anything else? All right, thanks.